Hello everyone. In this video, we're going to look at how to simplify radicals. Now, before we've looked at how to simplify radicals that just have a number underneath the square root, but now we're going to bump it up a little bit to where we have variables underneath there as well. And this time, it's not just going to be a square root, but we're going to have other roots like cube roots or fifth roots. And we'll look at how to simplify those. Before we dive into those example problems, let's actually just review what a radical is and what it means when we try to simplify or solve for a radical. Okay, so whenever you see a radical or a root, it's another word for a radical is a root. Okay, that just means this symbol here. A radical, when you encounter it, is asking you a question. Okay, and the question it's asking you to solve is this: which number can we multiply an index amount of times? Okay, now if you don't know the vocab for this, an index is the number that's sitting right on the perch of the radical here. Okay, so this particular radical is asking us the question: which number can we multiply 3 times, okay, 3 times, to itself? And this is really key, okay? Which number can I multiply to itself 3 times to get the radicand? Okay, and the radicand is the word that we use to describe the number that's inside of the square root, okay? So think to yourself for a second, what number can I multiply to itself 3 times to get 27? Okay, and you may know the answer to that, and I'll rewrite it here, but which number can we multiply by itself 3 times to get 27? And if your answer is 3, that is correct, okay? Because when you plug something like this into the calculator, right? Okay, if you plug this into Desmos, or if you have a calculator on hand right now, you would get the answer of 3, okay? So 3 is the number that answers that question, okay? Because if I do 3 times 3 times 3, I'm multiplying 3 times by itself. That's going to give me 27, okay? And I know that there's a lot of 3's here, but let's look at another example to really clarify this, okay? So in the first example here, the square root of 90. Now, you may or may not know this, but there actually is an index here that's invisible. And I'm not particularly sure why we make this invisible in math. I think it's just because we write square roots so much, it's easier to do less writing. But there actually is an invisible 2 that's right here as the index, okay? So when I encounter this radical, the question it's asking me is, which number can I multiply by itself 2 times to get 90? Okay. Now, if you were to take this and plug it into the calculator, you do get a decimal, so this is just to estimate, to say, let me see, if I plug this into the calculator now, the square root of 90 is 9.48, and then there's more decimals going on and on, okay, for forever. So you can test this out right now. If you take 9.48 and you can just take those first 2 decimals, maybe round it up to 9.49, multiply that by itself twice, okay? So 9.49 times 9.49, and you get a number that's really, really close to 90, okay? Now, it's not exact because we had to cut these decimals off at some point, but if we did have all of the decimals that went on and on with this, and I multiplied that by itself, I would get exactly 90. Now, our issue with radicals is we just really don't like decimals. We want our answers to be exact as much as possible and not have to cut off decimals or get an answer that is not the real actual answer by cutting it off at some point. So the square root of 90, since it gives us a decimal, all we're going to have to do is just simplify it and get an exact answer by simplifying. So I'm going to show you a strategy right now that actually it's different from what we learned in Unit 2, okay? I think it was Unit 2, Lesson 5, where we talked about simplifying radicals, and I showed you how you could do that using perfect squares. We're going to use a different method here just because it's going to be easier to use this method when we get to some of these problems where we have variables, okay? So here's how it goes. Okay. Sometimes part of it is a little bit easier, I think, in some ways. So all I have to do is think of two numbers, just two numbers that multiply to make 90. So probably the first two numbers that come to your head are 9 and 10, okay? Now, I don't have to put square roots over these like I did when I was doing perfect squares, but what I'm doing right now is I'm going to make a factor tree, and you may or may not have seen this before in previous math classes. So 90 splits into 9 and 10, and then I'm going to keep splitting. So now we'll come to 9 and think of two numbers that multiply to make 9. That would be 3 and 3, right? Come over to 10, 2, and 5. Now, when you're thinking of numbers to split into, just don't use 1 and itself. So I don't want to write 1 times 9 for the next two numbers, okay? Or 1 times 10. Now, the really cool part about this factor tree is if you know that you're done when you have prime numbers at the ends of your branches, okay? 3 is a prime number, 2 and 5 are all prime numbers, okay? So check this out. If I do 3 times 3 times 2 times 5, what does that make? 3 times 3 times 2 times 5, 90, okay? So what I did right now is I rewrote 90, this is still 90, but I rewrote it into its prime factors, okay? These are the numbers that multiply to make 90, therefore they're factors, okay? Because factors are just numbers that multiply to make another number, okay? Now, what I think the coolest part of this is that every number you encounter, every number, okay, has its own set of prime factors that are unique to it, okay? So 3, 3, 2, and 5, these factors, just like they are, just like this, no other number is going to have these prime factors. It's unique to 90. Only the number 90 has these prime factors, okay? Which is pretty crazy. Now, what we do once we find the secret code for your number, okay? This secret code that's unique to 90, is to simplify this, we're now going to look at the index, okay? So the index tells me that if I see a number twice, okay? If I see any number twice, I can actually remove it from the radical, okay? So obviously I see 3 twice, so I can remove that from the radical. Now, what I want you to really be careful of, because this is where people get messed up the most, when you remove this from the radical, do not write it like this, okay? So I don't want to take out 3 times 3 and put that outside of the radical. Instead, for every group that I'm able to take out, okay, I'm going to represent this with just 1 3, okay? And this will make more sense once we get to examples that have more groups that we're taking out. But for every group, I just take out 1 of those things in the group, okay? So if there were 2 2s, I would just take out 1 2. If there were 2 5s, I would just take out 1 5, okay? So that gets to be removed from the radical that's on the outside of it now, being multiplied. And unfortunately, 2 and 5, since there's not 2 of those numbers that are the same, they're going to stay inside of the radical. So I'm going to rewrite this multiplied together. So instead of it just being 2 times 5, I'll rewrite that multiplied together to be 10, okay? So I can rewrite the square root of 90, and I can simplify that to 3 square root of 10, which you should have practiced in Unit 2. This is just another strategy that we're going to be using to simplify, okay? So that would be our answer. Now, this strategy, again, like I said, really comes to fruition when we start doing example problems like the one we have over here, okay? Now, before we worry about the variables, let's just take care of the number here. So we know the index here. If we don't see an index, it's an invisible 2, right? So there's our index of 2. So see if you can remember what happens next. What do I have to do with 128? Okay, so I'm going to look at 128, and I just have to think of 2 numbers that multiply to make 128. Now, I don't know about you, but I think the easiest thing to do is if the number is even, well, I know that 2 times something else makes 128. And I can actually divide. So if I do 128 divided by 2, I get that other number, so 64. And I don't necessarily know that off the top of my head, but I can figure that out. If I know this is an even number, I can divide it by 2, and then figure out, okay, that multiplied together makes 128. Great. Now, what I'm actually going to do, because this factor tree is going to go on and on for quite a bit, I'm going to rewrite this over here so I have a little bit more room. So square root of 128, and so far that's going to split up into 2 times 64. And for this method, again, I don't have to write square roots over the top of this, okay? All right, let's keep going. So 2 is a prime number, so I will stop there. I can't break this apart any further, but 64 I definitely can. And we can continue doing the 2 thing. So 2 times 32, okay? So if I just take 64 divided by 2, that's where I get this 32 from. Let's keep splitting this up further. So 2, and then let's see, 16, 2 times 8, 2 and 8 make 16. And I can split up 8 to be 2 times 4, right? Okay, lots of 2's. And then finally, I can split up 4 into to be 2 times 2. Oh my gosh, all right. What I like to do, just so in case your factor tree just gets really crazy, I like to write all of the prime factors all together so we can see just how many 2's there are. So there's 1, 2, 3, 4, 5, 6, 7 of these. 1, 2, 3, 4, 5, 6, and 7. Great. This is the secret code that's unique to 128. Okay, so no other number will have these exact prime factors like this, okay? So this is unique to 128. Now, if you remember how this works, I need to find groups of 2. So if any number shows up twice, I can remove that from the radical, okay? So here's one group of 2. Here's another group of 2, and a third group of 2, okay? Now, for every group that I have, I'm taking out one of that number from the radical. So from this group, I'm just going to take out 1, 2, okay? From this group, I'll take out 1, 2. From this group, I will take out 1, 2. So all of those are going to go outside of the radical. So on the outside of the radical, I will have, I'll write it over here, 2 times 2 times 2. So 1 from each group gets to come out. Unfortunately, this guy is still trapped on the inside, so inside of the radical, I still have 1, 2 left over. And then let's go ahead and simplify this. So 2 times 2 times 2 is 8 square root of 2. Okay, so just with the numbers so far, I have simplified that to 8 square root of 2. And I'm going to leave some space here and here for when I do the variables next. Now, the variables I think are a little bit easier because they we don't have to do this crazy factor tree thing. We can just write this out as w multiplied by itself 7 times. So that's another way we can have w to the power of 7. We can write it like this, w times w, 4, 5, 6, 7. Okay, so this is another way to write w to the 7th power. And again, I'm going to go here and take out things in groups of 2. So one group of 2, another group of 2, third group of 2, and from this group I can take out one w. This group I can take out another w and a third w. Okay, so 3 w's get to be removed from the square root. Okay. Now, what's another way to write w times w times w? Well, that would be w cubed, w to the power of 3. And then I have one w that didn't make it out. He's left inside of the square root next to the 2. Okay. All right, so hopefully you're kind of catching on to this pattern. So see if you can guess what this next part is going to be. But I'll write this out completely so we can see. x times x times x times x. So I have 4 x's. I'm taking them out in groups of 2. So that's one group, another group. So from this group, I can take out 1x, and this other group, I can take out another x. So if I'm going to write this, x times x, I can write that as x squared. And thankfully for the x's, nobody got trapped inside of the square root. We were able to remove all of the x's, okay, with none left over. So this would be our final simplified answer. All right, take a second, pause this video, and see if you can figure out how to do 3 and 4 before I continue. So pause here and try them out. All right, let's go over 3 and 4 and see how they are done. Okay, so for number 3, now my index is 3. I'll worry about that in just a second, but first I'll start off by thinking of numbers that multiply to make 40. So maybe you might have thought of 4 and 10. Maybe if you thought of 8 and 5, that's totally fine, okay? Because at the end, you should end up with the same prime factors that are unique to 40. So let's see, 2 times 2, 2 times 5, great. So this is our secret code for 40 is 2 times 2 times 2 times 5, okay? Now, since my index is 3, I'm going to take out my answers in groups of 3. So there's only these 2 3s here that I see 3 times, okay? So for this whole group of 3, I can take out still just 1 2. Okay, so no matter how big your group is, so in a second we'll see an index of 5, just for that whole group, I'm only taking out 1 of that number inside, okay? So 1 2 gets to be removed, but that 5 is still left on the inside, so this should be my final answer. A lot of students commonly forget to write that index, like they transfer it over and they just forget to write that, so don't forget that this is still the cube root of 5. So there we go, that is my simplified answer. Now let's bump it up a little bit with this harder problem over here. So 243, yikes. So let me give myself a little bit of room. We'll separate this. I'll pull 243 off to the side. And now I'm thinking of 2 numbers that multiply to make 243. So this is not an even number, so I tend to like to go with the next biggest number up. So maybe it's divisible by 3. Let's check and see. So 243, is that divisible by 3? Yes, it is. Perfect. So that can split up into 3 and 81. And then 81, well, I know 9 times 9 makes 81. And then I can continue to split 9 and 9 up into 3 and 3 for that one 9, and a 3 and a 3 for the other 9, okay? So let me write this all out. I have 1, 2, 3, 4, 5 3s. Whew. All right, and that's exactly what I needed. I needed a group of 5, and that is my one group of 5. And so for that one group, I can remove 1 3, okay? So just a 3 all by itself outside of the square root gets to come out, and there's nothing left over, so whew, good so far. Next, the x's. So x times x times x, 4, 5, 6, and 7, okay? So I can take out one group of 5, and for that one group, I will take out 1x, and it looks like we'll have 2 x's that are still left inside of the radical. So that'll be x squared. Again, make sure that you write that this is a 5th root, so 5th root right there as our index. Alrighty, and then the y's are what's left over. So now that you've done this, maybe you've got the formula for 2 and 4. Maybe you see what we're doing here without having to write out the variable over and over again multiplied by itself. Maybe you can kind of just tell now that, hey, if I write out 8 y's, if I write out 8 y's, I can only take out one group of 5, right? I can take out one group of 5. And then how many would I have left over? I would have 3 left over, okay? And maybe if you don't see that, I can write that out right now, but 1, 2, 3, 4, 5, 6, 7, 8. And this is always a good way to double check if you're not sure. But yes, I can take out one group of 5 y's. So that would just be one y that I'm writing on the outside. And 3 are left over, okay? So every time you do one of these problems, especially with the variables, you're doing a division problem, okay? And I can just look at the exponents here. How many times does 2 go into 7? 3 times, and then there's a remainder of 1, okay? So your answer for your division problem goes outside of the radical, and your remainder goes on the inside, okay? So that would be our simplified answer for number 4.